Hello, so in this video we are going to talk through how to differentiate some functions with respect to x. Now notice that we say differentiate with respect to x. Now for your purposes you don't really need to worry about the fact with respect to x. All that literally means is that we've got a function like this, okay, so we've got y equals, okay, so that goes on our y-axis, and then we've got some function of x. So in other words, our input value is x, we do something to that input value, and then we get our output value y out. There are some other functions that exist that accept more than one input. So it might be x and z, or x and n and b, for example, okay? Well, in this case, we need to be clear about what variable we're differentiating with respect to. But in your case, and in fact all of the cases in this course, you're only going to get given a function with one input, and in this case the function input is x, which is why we differentiate with respect to that input, with respect to x. So just remember, how do we differentiate? Well, a couple of things you need to remember. First of all, if you get given a function of this type, okay, so it always needs to be written as some constant times x to some power, okay, so a is a constant and n is a power. If we've got it written like this, it's a two-stage process. Number one, we multiply by the power, okay, so multiply by the power. Then the second step is to subtract 1 from the power, okay, so subtract power by 1, okay? So in other words, when we differentiate, we should end up with dy by dx, and of course there's different ways of writing this, as an x to the power of n minus 1. So it's just a two-step process when we differentiate, okay? So let's start off with y equals x squared plus 3x minus 2, okay? And let's think about how to differentiate it. Now, I'm going to treat it term by term. So I'm just first of all going to look at the x squared. Now, first thing I'm going to write down is what my derivative is. So I'm going to write down dy by dx, okay? So I start with y and I'm differentiating with respect to x, so it's dy by dx, okay? Now, well, if I differentiate the x squared, I should bring the power down and multiply by that power, so I get 2x. Then if I reduce the power by 1, I get 2x to the power of 1, okay? Cool. Let's have a look at the next term. Well, look, this is 3x, so what's the power? Well, the power in this case is just 1, so it's 3x to the power of 1. Okay, so if I bring the power down, I get 3 times 1, which is 3, and it's positive 3. Then reduce the power by 1, I get x to the power of 0. Okay, cool. And then finally, if I look at my last term, well, look, at the moment, there's no x to the power of something. It's not written like this. So I need to kind of think about it. Well, if I just have a 2, what is the power of x? You're happy it's just 0. Because anything to the power of 0 is just 1. So effectively that last term, if I treat it as 2x to the power of 0, effectively just becomes 2 times 1, okay? So then if I bring the power down, I get negative 2 times 0, which is just 0, and then x to the power of negative 1. But I'm multiplying all of that by 0, which means that that final term has to also be 0 as well. Now I'm just going to tidy this up slightly. So my derivative function is going to be 2x plus 3. Okay, so that hopefully that makes sense. Let's have a look at the second one. So in this one, we're given that to find the derivative, so we're doing d dx of x squared plus 6 over x squared. Now, in this case, you notice that I'm writing it as d dx of this. Now, the d dx is just an operator. It just means differentiate with respect to x. Okay, so it's still differentiating. Now, first things first, I'm just going to rewrite this thing slightly, okay? So rather than having it as a fraction, so I'm going to look at the thing inside the brackets. Rather than having it as a fraction, I notice that a fraction just simply means divide. So in this case, I'm taking the numerator, which is x squared plus 6, and I'm dividing it by x squared, okay? So let's think about this. Well, if I'm dividing every term on the numerator by x squared, then I can also write it as a sum of individual fractions. In other words, x squared divided by x squared. And the 6 divided by x squared. That's literally the same thing. I'm just dividing everything on the numerator by x squared. Okay. Now, if I now differentiate this, well, first I need to do a bit of simplification because, of course, I need it in the form some number times by x to some power. Okay, so let's have a look at this. So x squared divided by x squared, well, that's just 1. Okay. And 6 over x squared, well, I need to rewrite it as some number, which in this case is 6, times x to some power. In this case, the power of x is negative 2. Have a look. Why is that the case? Well, look, if you notice that on the up here, I've got x squared on the denominator. I don't want that. I want x to some power. So in order to get it on the numerator, in order to get it as x to some power, I just remember that if I want to reciprocate my fraction, I can raise that to the negative power. Okay, that's the first thing that we did with indices. So now I'm in a position where I can differentiate. So let's have a look at this. So if I differentiate 1, well, just remember this is like 1x to the power of 0. And we've just seen that when I differentiate that, that should effectively just become 0. Okay? If I differentiate the positive 6x to the power of negative 2, that becomes, well, 6 times negative 2 is negative 12. And then if I reduce the power by 1, I get negative 3. Now, all I'm going to do is just look at how I got given it in. I didn't get given any negative powers at all, okay? So what I'm going to do is, instead of writing it as negative 12x to the power of negative 3, I'm going to write it as a fraction. So this should become negative 12 over x cubed. Remember that negative power just becomes a fraction, okay? Now, finally, so that's my final derivative. That's my derivative function. It's my gradient function. Now the last question looks a little bit scarier, but honestly it's just as straightforward as the other ones. You just need to think about your laws of indices a little bit more. So we have a fraction, 5x to the power 4 minus the 4th root of x cubed goes on the numerator. And on the denominator we have 10x squared. Okay, so first things first, I need to remember that if I want to differentiate this, I need it as some number times x to the power of something. So I need loads of terms just written as some number times x to the power of something. I can't just differentiate as it is. So first thing I'm going to do is actually separate this into two separate fractions rather than writing it as one. So I'm going to write this as 5x to the power 4 over 10x squared minus the 4th root of x cubed over 10x squared. So you notice what I'm doing is I'm dividing both terms on the numerator, so the 5x to the power 4 and the negative 4th root of x cubed, and I'm dividing it all by 10x squared. So now what I'm going to do is I'm going to focus on this root, okay? So I'm going to rewrite it. Instead of writing it as the 4th root, just remember that when I've got roots going on, I can write it as a fractional power, where the denominator of that fraction is effectively whatever root I'm taking. So in this case, what I have, well, I have 5x to the power 4 over 10x squared. That stays the same for the moment, okay? But then when I'm focusing on this 4th root of x cubed, I should be able to write that as x to the power of 3 over 4. And on the denominator, I have 10x squared, okay? So you notice that because I have the 4th root, and this is true of any roots, I should be able to write that as a power where it's a fraction and the denominator of that fraction is effectively whatever root I'm taking. So in this case, the 4th root, hence the denominator of the fraction becomes 4. Okay. So now if I have a look at this, I can now think, well look, if I'm dividing two powers by, or dividing a fraction with powers going on, I should just subtract those powers from each other. Just think laws of indices. So first things first, have a look. I have 5 divided by 10 in my first fraction. Well, 5 divided by 10 is a half, so I'm going to write that first. But then I'm going to have x to the power 4 divided by x to the power of 2. Well, you notice that if I'm dividing two things with the same base, I just subtract the powers. So 4 take away 2, that gives me x squared. If I focus on the same kind of thing going on in the second one, well, if I'm just going to pull out the numbers, notice there's a 1 on the numerator, so I get 1 divided by 10, so I'm going to write it as a tenth. And that's my number, that's my a if you like. Now if I focus on my powers, well, I have x to the power of 3/4 divided by x to the power of 2. That means that I just need to subtract these two powers from each other. So in other words, 3/4 take away 2. Now I am just going to write 2 as 2 over 1 to help it easier to look at fractions. Then to subtract fractions, I need to make sure I have the same denominator. So in order to have the same denominator, I'm going to basically multiply the second fraction by 4 over 4. Okay? So this thing should just become 3 over 4, take away 8 over 4. That's still 2 on that second fraction. And now all I end up with is 3 take away 8. Well, that is going to give me negative 5, and on denominator 4. Okay, so negative 5 over 4 is the fraction there, or the power there. So we get x to the power of negative 5 over 4. Now, this here now is ready to be differentiated. Okay, so all of that work was literally just to rewrite this horrible thing at the start as some number times x to the power of something, which we've successfully done now. So now I'm in a position to differentiate. Now notice the notation I'm going to be using here. Okay? Because I was given f of x in my question, I'm going to write my derivative as f prime of x, okay? You could write, if you want, dy by dx. However, the issue with writing dy by dx as opposed to f prime of x is that you're assuming that f of x is y, okay? So you're letting y equal f of x, okay? Whereas if in this case, because we've given a function, f of x, I'm going to write derivative as f prime of x. So let's have a look. Well, I'm going to focus on my first term. So if I bring the power down, I get half times 2, that's just 1. Then I reduce the power by 1, I get x to the power of 1. Well, that's just x. So it's 1 times x to the power of 1, which is just x. Now if I focus on my second fraction, well, have a look. If I bring the power down, I get negative 1/10 times by negative 5/4. You can write that down if you like, but it should be just multiply across the numerators, multiply across the denominators, and find it comes out as positive. Well, it'll come out as positive 5/40, which can simplify down to 1/8. Okay, so it's positive 1/8. Then if I reduce the power by 1, I get x to the power of negative 5/4. Reduce that negative 5/4 down by 1, that becomes negative 9/4. Okay? Then my last job is just to think, well, look, I wasn't given negative powers in my question, so I need to rewrite it. So I don't have negative powers anymore. So in other words, I need to consider fractions instead. So I'll end up with x, that stays the same, but then I end up with 1/8 times by 1/x to the power of 9/4. And you notice that x to the power of 9/4 can be rewritten again. So I can write that, just using my roots, as 1/4 root of x, all raised to the power of 9. And that's, of course, all multiplied by 1/8, so not add, times by 1/8. And then I can just finally smush together these two fractions on the end, multiply across the numerators, multiply across the denominators. I get 1/8 to the 4th root of x to the power of 9. So that should be my final answer fully simplified.